Alright, good morning, calculus geniuses. So we're going to do a little quick video on implicit differentiation. And implicit differentiation is, well, sounds confusing and complicated, but it's actually not all that bad once we understand the very first piece of this. So we know it's easy enough to take the derivative when we have an unknown function such as y equals 4x squared plus 2x plus 1. But it's not so easy if we don't actually know what the function is. We're just told that we have a function and it's called y. And how do we find out the derivative of that? Well, again, since we don't really know what y is equal to, we know that there's a function there somewhere, and because we see a y there, it's implied that y is equal to something, some function, so that's where we get the name implicit differentiation. So we don't know what the y will equal, or is going to equal, or is equaling now. However, we'll be able to sort that out later, most of the time, and sometimes we can't, and that's still okay. So the reason it's called implicit differentiation is because the function that's supposed to be here is only implied. We don't know exactly what it is. Just like when you imply something, you don't say it directly, you say it indirectly, or just kind of leave it unsaid but hinted at. So what do we do when we have just a y and we don't know what the function is? Well, we use some notation. We write either dy dx for the derivative of y, or we write y prime. And for today, I'm going to write dy dx, even though y prime is perfectly nice. So let's do a little quick comparison here. So here we have this expression here, this function, 2x plus 1, and it's cubed. And we want to find the derivative of this. Well, we know that we need to use the chain rule. So we bring down the 3 times the 2x plus 1, leaving the function on the inside the same, reducing that by 1, and then we multiply by the inner function, which in this case, or the derivative of the inner function, which is just in this case 2. And then we clean that up a little bit. 2 times 3, she is 6 times 2x plus 1 squared, and we're done. That's easy enough. We already know the chain rule pretty well. But what happens if we have just y being cubed and we don't know what the function is? Well, that's okay. We just use the notation bit. So y cubed is really the same as some function cubed, just like we have right here. So we just do the exact same thing. So we bring down the exponent in front. We leave the expression on the inside as it is. We reduce the exponent by 1. And then we multiply by the derivative of the inside function, which we're just going to call dy dx. Now we don't know what the derivative of the inside function is, but we can call it dy dx, and that will be able to serve our purposes, and we will see much more of that later. So we're just going to use this notation here, and that's really all this is. It's a little complicated sometimes, but we'll manage to get through. So here's our first example, and this one's as straightforward as we can possibly get. So we just do the derivative of each of the pieces. So the derivative of, well, actually, let me say this first. Essentially, all of these implicit differentiation problems will be given in equation form. So we'll have an equation of x's and y's, and usually equal to some number, or maybe it could be equal to also x's and y's, but it's always an equation. So we're going to take the derivative of the first part of the equation, which is obviously 4. And the derivative of 3y, we know that 3 is just a constant multiplier, so we just need to find the derivative of y. Again, we don't know what the derivative of y is because we don't know what the function y is, but we can use the notation. 3 times dy dx. And the derivative of 12, of course, is 0. Now, we don't have our derivative solved for yet, but that's easy enough. All we need to do now is just solve for dy dx. So we're going to subtract 4. So we have 3 dy dx equals negative 4. And then we divide both sides by 3, and we have dy dx equals negative 4/3. And we are done. So there's our first implicit differentiation problem. And as we can see, we didn't even need to know what the function was of y. It is some function, we just don't know what it is. But we were able to find out the derivative of that function even though we didn't know what it was. Turns out it's negative 4/3. So there's our first implicit differentiation problem. So our next one is slightly more complicated, but not very much more complicated. So we're just going to, again, do the derivative of each of the pieces. So the derivative of 5x squared, of course, is 10x. The derivative of 2y is just 2 dy dx. And the derivative of 10, of course, is just 0. And again, we're going to solve for dy dx. And I'm just going to do these two steps without actually writing them all down. So we're going to subtract 10x from both sides. So we got 2 dy dx equals negative 10. Divide both sides by 2, and we get dy dx equals negative 5x. And we're done. And again, we didn't know what the function was for dy dx, we didn't know what the function was for y, but we do now know what its derivative is, negative 5x. So we could probably assume that the function was maybe negative 5x squared over 2. But that's a story for another day. All right, so a little more complicated to put an exponent on y in this case. So we're just doing the derivative of the first piece. Derivative of 6x is just 6. Now here we have the chain rule because we have a function y raised to a power. So we need to apply the chain rule here. So we bring down the 2, keep the y as is, reduce it by 1, and then multiply by the derivative of the inner function, which in this case is just dy dx. And that's equal to 0. So now we have to solve for dy dx, so we'll subtract 6. So we have 2y. I'm going to start writing y prime because it's going to save me a little space and a little time here. So instead of writing dy dx, I'm just going to start writing y prime now. Equals negative 6, and then divide both sides by 2y. So we get y prime equals negative 6 over 2y. And if we reduce that down just a little bit, we get negative 3 over y is y prime. So again, just going through this process, we're able to find the derivative of y, even though we didn't know what y was. So let's move on to, oftentimes this is kind of the first problem that's given, and this is just a circle as we know. And so we'll just rip through this the same way we have been. So the derivative of the first part is 2x. The derivative of the second part, again, this is a chain rule, so we bring down the 2 in front, leave the inner function as it is, because really this is inner function is y to the second power, and then we multiply by the derivative of the inner function, which is just y prime. And the derivative of 16, of course, is 0. So now we need to solve for y prime, because that's what we're always trying to do here, find the derivative. So we're going to subtract 2x, so we get 2y, y prime, equals negative 2x. And then we divide both sides by 2y, and we get y prime equals negative 2x over 2y. And when we simplify that, we see that y prime is just negative x over y. And let's just stop for a moment here and take a look at our answer. So we see that the derivative of y prime, is equal to negative x over y. And generally our derivatives don't include the y variable, or the y function in this case. Usually it's just in terms of x's only, but because we're not able to figure out what y is equal to, we can still just say, hey, y is still here, it's still a function, we just don't happen to know what it is yet. And there are methods that we can use to, in some cases, find out what y was, but this is not going to be one of those cases, and we're not going to be using those methods right now anyway. So again, our derivative here generally includes only x's, but now with our implicit differentiation, oftentimes our derivatives include x's and y's. All right, so let's move on to the next problem. This one looks a little more complicated, and it is. So we have y cubed plus y squared minus 5y minus x squared equals negative 4. And again, we're just going to go through and we're going to take the derivative of each of the pieces. So the derivative of y cubed is 3y squared times y prime. The derivative of y squared is 2y, y prime. The derivative of 5y is 5y prime. The derivative of negative x squared is negative 2x equals 0. So you'll notice in all the previous problems, we've had only one y prime to deal with. And here we have actually 3 y primes to deal with. So the question is, how do we turn 3 y primes into 1 y prime? And the answer is by factoring, because you'll notice that each of those 3 terms has a y prime in it. But before we factor, we're going to make sure that only the y primes are on the left side, and we'll move everything else over to the right side, which in this case is just the 2x. So we're just going to put the 2x over to the other side. So we got 3y squared y prime plus 2y y prime minus 5y prime equals 2x. So we see we only got y primes on the left side now. And so now we see that there's each of the three terms has a y prime, so we can factor out the y prime. So we have y prime is 3y squared plus 2y minus 5 equals 2x. And so now we see that y prime is almost by itself. All we need to do is just divide by that one term right there. So now we got y prime equals 2x over 3y squared plus 2y minus 5. And the moral of the story here is that when we have multiple y primes, the only way to get them into a singular y prime is to factor it out. That's our important lesson out of this particular problem. And so far, we've only used the power rule, but here we get a chance to use the product rule. So we got xy equals 12. So we're just going to use the product rule because we have two things being multiplied together, x times y. So we have, applying the product rule here, we have the first times the derivative of the second. Again, we don't know what y is, but we can say the derivative of y is just y prime, plus the second times the derivative of the first. So we got y times, and the derivative of x, of course, is just 1, equals 0. And again, our job is to solve for y prime. So we're just going to subtract y and divide by x, and we're going to have y prime equals negative y over x. These are all actually pretty simple, but implicit differentiation is a powerful tool that allows us to find derivatives of functions that we don't even know what they are, and it also allows us to solve what are called related rates problems, which are coming up not today, but soon. All right, so here we have 4x cubed y equals 24. Same kind of situation, still got a product rule going on here, but a little bit more complicated. So again, we do the first times the derivative of the second plus the second times the derivative of the first. So that's going to be 12x squared equals 0. And again, we're just going to solve for y prime here. So we're going to subtract 12x squared y over. So we got 4x cubed y prime equals negative 12x squared y. And then we're going to divide both sides by 4x cubed. So we can get y prime by itself. And so we end up with y prime equals, so negative 12 over 4 is negative 3. Cancel the x's, so that leaves us with an x on the bottom and a y on the top. And in this case, because there was only one y prime, we didn't have to do any factoring to get it into just the one y prime. So let's move down here, and again, slightly more complicated. This time the exponent is on the y, so that means we're going to have a little chain rule going on here. So applying the product rule, because the product rule applies to all of the expression, as opposed to the chain rule just applying to this piece right here. So again, we have the first times the derivative of the second plus the second times the derivative of the first. Again, equals 0. And again, we're just solving for y prime, which means we'll subtract the 4y cubed and divide by the 12xy squared. So subtracting that and dividing by that, and we get y prime equals negative 4y cubed over 12xy squared. And then we notice that we have multiple y's here, so we can cancel off two of the y's up here and two of the y's down there and reduce here. And so we have negative y over 3x is y prime. So y prime equals negative y over 3x. Okay, so we're getting close to done. on this page, it wouldn't be a calculus day without, hold on, sorry, last page. Last page has the trig functions. Okay, so again, we're here a little bit more complicated. So we got a product rule, and so again, we're just going to find the derivative of each of the pieces. So the derivative of x squared, of course, is 2x. And then we got the product rule, 2xy. So I'm gonna look at it this way. We got 2x times y. Those are the two things being multiplied together. So we have the first times the derivative of the second plus the second times the derivative of the first. And then we're on to the chain rule for y squared. I know it just looks like a power rule, but it really is a chain rule because y really is a function. So we're going to do the derivative of y squared, which is 2y. So we bring down the exponent in front, keep the inner function as it is, and then multiply by the derivative of the inner function equals 0. And so you notice we have a y prime here and a y prime over here, which means that we need to do some factoring. So move everything over to the right side first, and then factor out the y prime. So we have 2x y prime plus 2y y prime equals, subtracting this and subtracting that, we have negative 2x minus 2y. And then we're going to factor out a y prime. So we have over here y prime times 2x plus 2y equals negative 2x minus 2y. And then we divide everything by 2x plus 2y, and we get y prime equals negative 2x minus 2y over positive 2x plus 2y. And then the last thing we do here is just divide everything by 2, and so we're left with y prime equals negative x minus y over x plus y. And we're done, because we know we can't cancel out any of those x's and any of those y's. Okay, so this one I left a lot of room for. I'm not sure we're actually going to need all this room. So here we have a product of x and y inside a cube root. So first I'm just going to rewrite that as xy to the 1/3 power. Everything else stays the same. And now we just do the derivative of this using the chain rule, and inside the chain rule we're going to have a product rule. So the chain rule says bring the exponent down, leave the inner function as it is, reduce the exponent by 1, and now multiply by the derivative of the inner function, and the derivative of the inner function really requires us to use the product rule. So we got the first times the derivative of the second plus the second times the derivative of the first. And the derivative of x, of course, is just 1, and the derivative of 4y is 4y prime. So as I'm looking at this problem, I'm finding myself a little unsure of how I'm going to proceed right now in terms of getting the two y primes together without making a bigger mess. So what I'm thinking about is how I can get rid of this piece right here and drop it down to the bottom. Oh, I can distribute, that's what it is. Okay, good. Right, this is going to be a mess. Alright, so I'm just going to distribute this piece right here into here and here so I can break the y prime out of this parentheses. So, good thing I left a lot of room. And I'm trying to decide whether I'm going to drop the negative 2/3 down to the bottom. And I think I'm not going to. So I'm going to write this as 1/3 xy to the negative 2/3 times xy prime plus, same thing again now, times y, 1/3 xy to the negative 2/3 times y equals 1 plus 4y prime. Well, this is just going to be very unpleasant. Okay, so I'm going to move the terms that that have the y prime over onto the left and all the other terms over onto the right. So that means I'm going to subtract this whole term here and subtract the 4y prime over to here. So we have 1/3 xy to the negative 2/3 xy prime minus 4y prime equals 1 minus 1/3 xy to the negative 2/3. So again, just putting all the y primes on one side and everything that doesn't have y prime on the other side. So now we can factor out a y prime here. So we got y prime times this mess right here. 1/3 xy to the negative 2/3 x minus 4 equals 1 minus 1/3 xy to the negative 2/3. And then we can divide this by that, and for time-saving purposes, I'm just going to call that simplified, even though we should certainly do more simplifying than that, but I'm not going to go through all the algebra right now to do that, so that we can save time on the video, and because I've run out of room on my paper. To negative 2/3, so that's the right side, put that over that, 1/3 xy to the negative 2/3 minus 4. And there is our y prime, not quite fully cleaned up and simplified, but we get the idea. Okay, so that was a little complicated. In order to break the y prime out of this term right here, we had to distribute first, so the parentheses were gone, and then we could move the things around, so all of the non-y prime terms went to the right, and all the y prime terms went to the left. Okay, as promised, we have some trigonometry. Wouldn't want to have a calculus class without some trig. Okay, so we got sine x plus cosine y equals 2. No difference between this and the other stuff. The approach is still the same. So we do the derivative of sine x, which is cosine x, plus the derivative of cosine y, which is negative sine y times y prime equals 0. And now we want to solve for y prime. So we're going to subtract the cosine of x and divide by negative sine. So y prime equals negative cosine of x over negative sine of y. And it seems tempting, because we got a cosine over a sine, to say, oh, that must be a tangent or a cotangent. But this is an x and this is a y, so we can't really put that together. But we can get rid of the negatives. So y prime equals cosine x over sine of y. So there it is. Again, all we're just doing is using the notation for y prime and then solving for y prime. Same kind of trick here, though this is a product rule. And we got a 3 here, a constant multiplier of 3. So again, I'm just going to treat this. I'm going to keep the 3 with the first part. So we have, so the first times the derivative of the second. So times negative sine of x plus the second cosine of x times the derivative of the first. So it's going to be 3 cosine y. 3 cosine y times y prime equals 0. So again, we have one term that has a y prime. So we're going to, in this case, add this over, and this is sine x and this is sine y, so we can't even put them together. So we're going to add over the 3 sine x sine y and clean this up a little bit. So we have 3 cosine x cosine y y prime equals 3 sine x cosine y, sine x come on now. So add sine x sine y, there we go, sine y. And then we divide both sides by 3 cosine x cosine y. So we get y prime equals 3 sine x sine y over 3 cosine x cosine y. And now we see we have a sine x over cosine x and a sine y over cosine y. And so those are both tangents, and the 1 or the 3's turn into a 1. So we have y prime equals tan x times tan y. Tan x times tan y. And we're getting close to done. So now we have tan y equals y minus x. So we do, the derivative of tan is secant squared y times y prime. The derivative of y is y prime, and the derivative of x is just 1. So again, we have two y primes, so we need to move this y prime over to there. So we're going to have secant squared y prime minus y prime equals negative 1. And we'll factor out the y prime. Secant squared y minus 1 equals negative 1. And then we divide both sides by secant squared y minus 1. And we have y prime equals negative 1 over secant squared y minus 1. Just remembering, of course, that the derivative of tangent is secant squared, and everything else is just the same procedure, getting all the y primes on one side and factor them out. And here's our last one. We have the cosine of the product of some things, x and y. So our approach is still the same. This is going to be a chain rule problem with a product rule on the inside. So the derivative of y is just y prime. The derivative of cosine is negative sine. Leave that as is. Times product rule. So first times the derivative of the second plus the second times the derivative of the first. Derivative of x is just 1. And so again, we see that we have a y prime inside a parentheses. That means we're going to have to distribute this to break the y prime out of the parentheses, move it over there, and factor it out. So we got y prime equals negative sine of xy times xy prime plus, actually, minus, because that's a negative sign, sine of xy times y. So now we're going to subtract the y prime term over. Actually, we're going to add the y prime term over. So y prime plus sine of xy times xy prime equals negative sine of xy times y. And then we're going to factor out the y prime and put the x in front there so it's a little less confusing. So we're going to have y prime times the 1 from there. And we bring the x over there in front, plus x sine of xy. And equals, I'm going to bring the y over there too, so negative y sine of xy. And the last piece is just to divide both sides by 1 plus x sine of xy. So y prime equals negative y sine of xy over that whole mess right there, 1 plus x sine of xy. And I think that is done. Okay, so there is your quick video, although it's not as quick as I thought it was going to be. I thought it was going to be like 15 minutes. It was twice that length, so it's 29 minutes. And so here is your mission, which I'm going to put on the clipboard here, and I'm going to turn the paper sideways, but it'll still be right side up in the camera. Write it in red. So it's page 151, 1 through 14. So I just did a whole bunch of those problems. I did about 14 problems just now, give or take a little bit. And I was explaining each one of them, so hopefully it'll take you a lot less time. So there's your assignment. Good luck.